experiment is based on Gauss law of magnetism. What we're going to achieve is we're going to build a Gauss gun with the theory behind it is Gauss law of magnetism. What it actually states that, from what you can see here, the net magnetic flux out of any closed surface is zero. If you don't understand, it's okay, I'll explain to you. This set here is actually obeys Gauss law. How so? When the balls, steel balls, attached to the magnet is actually already in equilibrium. When it's already in equilibrium, there's no force, there's no force. That means net force is equals to zero. That means there's no transfer of energy, there's no nothing, it's like zero. What we're going to try and do is, we'll take one steel ball here, we'll give it a push, a certain force, let's say. When it travels here, we'll have, before it hits, we'll have U1. Before it hits, it's still in equilibrium. When it hits, it becomes chaotic. Extra energy is inputted in the system. When an extra energy is inputted, from Gauss law of magnetism, it states that it must be zero some way. So when the extra energy, the energy will be transferred to the last ball where it's where it's loosely attracted. So it will be detached from here and move with V1. When it detaches from this ball, the V1 is equals to U1 if we assume that there's no loss of energy. When the steel ball reaches just before it hits the second magnet, the V2 is actually higher than V1. Why is that so? That is because the second magnet here attracts the steel ball. It actually pulls the steel ball, which increases the velocity, which then increases acceleration. When it hits the second ball with the second magnet with the V2, this will leave with V3, which is same as V2, same as the first set. Now this will go by, as how I explained here, it will go by the same until the last ball here. The last ball will have V4, which is way higher than its initial U1. Now how high, you can ask? By calculation, by using Ke is equals to half mv squared, it will be 4 times higher. The velocity will be 4 times higher than the initial velocity from here. Now, this Gaussian trap is similar to another application. It's called Newton's cradle. As you can see here, the 4 balls here. Now what I'm trying to do is, let's say there's another ball here. Put it to this side. When I let it go, the PE will convert to Ke. And when it hits here, the extra energy is inputted. When there's extra energy, it will somehow try to balance it back. What happens? This ball go here with the exact edge. If same as here, if we consider there's no loss in energy, Ke is equals to PE. So basically the same thing here. The transfer of momentum is applied here as well. The ball here hits the U1 and leaves with V1. So M1 V1 is equals to M2 V2. Now we come to Newton's laws. This Gaussian track or Gaussian gun follows Newton's first law. That's how basically Newton's first law is initial. To explain it more further, when let's say an object moves in a constant velocity, it will never stop or change in direction if there's no external force acting upon it. Now here, the acceleration increases because there's a force, external force, which is the magnetic attraction. So Newton's first law applies here as well. Newton's second law, change in momentum. Now momentum is P is equals to mv. So change in momentum, that means dp dt is equals to dm, using chain rule, dm dt v plus dv dt m. Since there's no change in mass, because the change in mass only occurs when you go in the speed of light. C is equals to 3 times 10 to the power 8 meters per second. But since we are not going in speed of light, dm dt is equals to 0. So dp dt is equals to dv dt m. What is actually meaning is F is equals to ma. It's m here, AC. So Newton's second law. Net force must be 0. That means F is equals to 0. Ma is equals to 0. Must be like that. Now, Gauss law of magnetism also, if you see it in equation form, is actually integration closed loop, important. B is I think something magnetism, Tesla I guess. Vector dot dA is equals to 0. Now Newton's third law, every action has an equal and opposite reaction. That is quite simple. You can easily see it here. When a ball hits, ball leaves. Every action has an equal and opposite reaction. U1 is equals to V1. The initial velocity is equals to final velocity. The velocity of the ball which hits the magnet is equal to the velocity of the ball leaves the magnet. So from here I'll explain every single part, every single aspect that's actually linked to Gauss law of magnetism, which therefore linked to Gaussian track. So yeah.
The assumption of our experiment about Gauss law has been classified into 5. The first one is verifying that the Gauss law is working completely with our experiment. The second one is as the distance between sets of magnets and metal balls increases, the velocity of the last ball which is departing the table increases as well. The third one is the friction force between the steel balls and the table is completely negligible. Fourth one would be the assumption that there is no air friction involved in our experiment. The fifth and the last one, that we assume that there is no loss of energy during the transfer of energy between the metal balls and magnets. So these 5 are all our assumptions. Thank you, that was all.
So first off, we set up the experiment by using 2 plywoods. We placed 2 plywoods on the table, and in order to stabilize it, we use cellophane tips, hence forming a linear track. During the first stage of the experiment, we actually use 2 extremely powerful neodymium N48 magnets, and attached to the magnets are 4 balls. Why 4 balls? Because the balls will be loosely held. If more than 4 balls are placed, the energy transfer to the balls between the balls would not be that efficient. And also, to keep the initial speed constant and reduce its uncertainty, we push the trigger ball slowly. And the distance between the trigger ball and the magnet is 5 cm. Speaking of the second stage of the experiment, we used 2 sets of magnets, each of them attached to 4 steel balls, and distance between the magnets is 7 cm. And the trigger ball, as usual, is 5 cm away from the magnet. Moving on to the third stage, now we use the 3 sets of magnets, and as usual, each of the magnets are attached to 4 steel balls, but this time we reduce the distance between the magnets to 5 cm, and the trigger ball remains 5 cm away from the magnet. Speaking of the fourth stage of the experiment, we used 4 sets of magnets, and as usual, each magnet is attached to 4 steel balls, but this time we maintain the distance between the magnets to be 5 cm, and the distance between the trigger ball and the first magnet is 5 cm. That's all for the experiment part. Thank you. So basically I'll be explaining how we did our measurements. This is the steel trigger ball, 5 cm away from the magnets, which is attached to 4 steel balls. And once the trigger ball is pushed, the steel ball departs and makes a horizontal projection and falls onto the carbon paper, which then makes an imprint on the A4 paper below the carbon paper. So basically, the way we measure the distance from this is, first we measure D1, that is the horizontal distance between the edge of the table and the edge of the carbon paper, and the D2 distance will be basically the distance made by the steel ball's imprint on the A4 paper, and the total distance D will be D1 plus D2.
So basically what we get out of our experiment is this table actually. We got 4 stages of experiment. For each experiment, for each stage we did 5 trials to get this average velocity out of each stages. So as you can see, as the stages are increasing, the velocity is increasing as well. So the way we actually get this velocity, so our average velocity is based on these 2 equations. The first one is the v horizontal, which is equal to d total over t. The second one is s equals to ut plus half at squared. In this equation, u, which is the initial vertical velocity, is equals to 0. So after all this, we're going to come up to this equation, which is 1 over 2 at squared. After that, as you can see, solving this equation for t, we will get set 2s over g, assuming that s equals to h, which is the height of the table, a equals to g, which is 10 meter over square. We will get d total over t out of this equation. D total over t equals to set 2h over g. So solving this equation for d total, we will get d total over set 2h over g equals to v. So we will get v equals to d set g over 2h. This is the exact way that how we got average velocity for each of our stages.